So let's find the maximum flow of the computer network model below the transmit data from computer A to computer Z. So certainly, let's find the maximum flow of the computer. So first step, so let's figure it out by step-by-step process. So first step is the identify the source and the sink. So the source node is the computer A and the source node is sink node is the computer C. So the step 2 is to find the initial flow. So start with an initial flow of 0 on all edge. So that is the initial flow of all edge. So the step 3 is find an augmenting path. So what is an augmenting path? So augmenting path is a path from source to the sink that has available capacity on all edge. So in this network, in this problem, one possible augmenting path is A to B to D to G and to C. I repeat, A, B, B, D, D, G, G to Z. So A, B, D, G, Z. The maximum capacity along this path is 5. So edge G to Z. Increase the flow of this path is by 5 units. So for the next step, update the residual graph. So for this, create a residual graph to track the remaining capacity in each edge. For the following edge from source to sink, or I repeat, the source to the sink and the augmenting path, subtract the flow from the capacity. So for each backward of the edge, from sink to the source and the augmenting path, so add the flow to the capacity. So for the step 5, repeat step 3 and step 4. Find another augmenting path and residual graph. For example, you could find the path like A, C, G, A, C, F, H, Z. That's it. A to C, C to F, F to H, H to Z. A, C, F, H, Z with a capacity of 4. So update the flow and residual graph accordingly. So for step 6, continue until no more augmenting paths exist. Keep finding and updating augmenting path until no more path can be found. So for the step 7, the final step, calculate the maximum flow. For this, the maximum flow of the sum of the on all edge leaving the source node or entering the sink node is like this. For visualizing the process, while it's difficult to visualize the entire process here, you can also use tools like online network flow solver or graph drawing software. So for this, in this case, the edge leaving node A are A to B with the flow of 5. So A to C with the flow of 4. So therefore, the maximum flow is 5 plus 4 is equals to 9 units. So the final answer is the computer network can be transmit data from computer A to computer Z to a maximum rate of 9 units. That's all. Thank you. So hello everyone. So let's find the shortest path from vertex starting vertex. So let's assume it's A. So to all other vertex in the given network graph. So first is the distance array. It's create an array to store the shortest distance from the starting vertex to each vertex. So initialize here all vertex with infinity except for a starting vertex distance which is 0. So the distance is A is equal to 0. So from B, C, D, E, F there are their distance is infinity. So visit array, create an array to keep track visited vertices. Initialize all vertices are unvisit. So for the second step is find the vertex with the minimum distance. Select the vertex with a small distance from the starting vertex that hasn't been visited yet. So mark the vertex as visited. Mark the selected vertex as visit. Iteration of here. So vertex A is distance 0. So mark A as visit already. So update the distance from B is equals to 2, and then C is equals to 4, and then D is equivalent to infinity, also E and F. So for this, update the distance of an adjacent vertex for each unvisited neighbor of a selected vertex. So calculate the tentative distance from the starting vertex through the selective vertex. And all tentative distance is smaller than the current distance of the neighbor. Update the distance in the distance array. So the step 3 is to repeat. So repeat step 2 and 3 until all vertices have been visited. So for iteration 2, select vertex B, distance 2, mark B as visit already. Update the distance. So C is equals to 3, D is equals to 6, and E and F is still an infinity. So for this, so let's select the vertex C, distance 3. So mark C as visit already. Update the distance C. So D is equals to 5, E is equals to 6, and F is still equals to infinity. So as I said, repeat and repeat. So select vertex D. So the distance of vertex D is distance 5. So mark D as visited already, and then update distance. So E is equals to 7 and F is equals to 7. So for that, there's still iteration. So select vertex E. So the distance is 6. Mark E as already visit, and then update distance. F is equals to 7. So as that, mark F as a visit already. So the 7. Then still another, select the F, and then its distance already, distance 7. Mark F as visit. So final shortest distance is A is equals to 0, B is equals to 2, and C is equals to 3, D is equals to 5, E is equals to 6, and F is equals to 7. So for these, to find the actual path from track back using the update distance, note this is general explanation of this trash algorithm, or Dijkstra's algorithm. So that's all. And as I repeat, the final shortest distance is A is equals to 0, B is equals to 2, C is equals to 3, and then D is equals to 5, E is equals to 7, and lastly, F is equals to 7. So thank you.
First is to find the maximum flow of the transport network given below. Image represent a transport network where nodes S1, S2, S3, S4 are source and node T1, T2 are zinc. And the network has a capacity which represents the maximum amount of flow that can pass through that edge. To find the maximum flow that can be represented from the source to the sink without extending the capacity of any edge. The maximum flow for this network is 19 units. This means that we can send a total of 19 units of flow from the sources to sinks without breaking any capacity contained. S1 to A have a 3 unit, second A to P1 9 unit, S2 to B 4 unit, B to E 5 unit, S3 to C 11 unit, C to E 6 unit, P1 11 unit, S4 to D 3 unit, P2 4 unit, C2 P2 2 units. The total flow entering a node is equal to the total flow leaving that node except for the sources and links. The flow on each edge does not exceed the capacity of that edge. Next is to find the shortest path of each node from the starting vertex. Graph. We'll assume that the graph is direct as the arrow indicates a specific directions for traversing the edge. The number on the edge represents the weight or cost associated for traversing that edge. S to A. The direct path S to A has a weight of 20. This is the shortest path to A. Is S to B. The shortest path is S to A to B with a total weight of 20 plus 7 equals to 27. S to C. The shortest path is S to A to B to C with a total weight of 20 plus 7 plus 0 equals to 27. S to D. The direct path S to D has a weight of 3. This is the shortest path to D. Next is S to E. The shortest path is S to E with total weight of 20 plus 1 equals to 21. Next is S to F. The shortest path is S to A to B to C with F with total weight of 20 plus 7 plus 0 plus 5 equals to 32. Is S to G. The shortest path is S to D to G with a total weight of 3 plus 6 equals to 9. S to H. The shortest path is S D G H with a total weight of 3 plus 6 plus 4 equals to 13. Is S to G. The shortest path is S to D to G with a total weight of 3 plus 6 equals to 9. S to H. The shortest path is S D G H with a total weight of 3 plus 6 plus 4 equals to 13. Negative edge weight will represent Dijkstra algorithms would not be applicable and other algorithms like Fillman-Ford would be needed.
Find the maximum flow of the transport network given below. So step 1, define the problem. We need to calculate the maximum flow from the source node S to the sink node. This is achieved by finding paths through the graph and distributing flow along them while respecting edge capacities. Step 2, identify the first augmentating path. Use breadth first search or visually inspect to find a path with available capacity from S to the sink. So, in path 1, we have S to top left, to middle right, and to sink. So, capacities along the path, we have S to top left is 8, top left to middle right is 4, and middle right to sink is 11. So now, the bottleneck or the minimum capacity is 4. The update flows is subtract 4 from forward edges in the path. Add 4 to reverse edges. In step 3, update residual graph. S to top left becomes 8 minus 4 is equal to 4. Top left to middle right becomes 4 minus 4 is 0. Middle right to sink becomes 11 minus 4 is 7. Step 4. Find the next augmenting path. In path 2, we have S to bottom left, to middle right, and to sink. We have the capacities along the path. We have S to bottom left is 10. Bottom left to middle is 6. Middle to middle right is 5. And middle right to sink is 7. Now, the bottleneck or the minimum capacity is 10, 6, 5, 7 is equal to 5. And the update flows, subtract 5 from forward edges and add 5 to reverse edges. In step 5, upgrade residual graph. S to bottom left becomes 10 minus 5 is 5. Bottom left to middle becomes 6 minus 5 is 1. Middle to middle right becomes 5 minus 5 is 0. Middle right to sink becomes 7 to 5. 7 minus 5 is equal to. Step 6. Find another augmenting path. In path 3, we have S to bottom left, to bottom middle, and to sink. The capacities along the path is S to bottom left is 5, bottom left to bottom middle is 8, bottom middle to sink is 22. So the bottleneck or the minimum capacity is 5, 8, 22 is equal to 5. The update flows. Again, subtract 5 from forward edges. Add 5 to reverse the edges. Step 7. Update residual graph. S to bottom left becomes 5 minus 5 is 0. Bottom left to bottom middle becomes 8 minus 5 is 3. Bottom middle to sink becomes 22 minus 5 is 17. Step 8. Stop when no more augmenting paths exist. At this point, no more paths from S to the sink exist with available capacity. So, in step 9, here we are to calculate the maximum flow. Add the flow values out of the source S. So S to top left is 4 and S to bottom left is 5 plus 5 is equal to 10. So now our maximum flow is 4 plus 10 is equal to 14. From the starting vertex. To solve this step by step, we will apply Dijkstra's algorithm to find the shortest path from the starting vertex or node 0 to all other nodes. Let's break it into steps. Step 1. Initialization. Set the starting vertex as node 0. Number 2, assign the initial distances to all nodes. So we have distance to node 0 is 0 all nodes as unvisited. Step 2. Process node 0. Number 1. The current node is 0 with distance is 0. Number 2. Update the distances to its neighbors. So we have node 1. The distance is equal to 0 plus 4 is 4. The node 4. We have distance is equal to 0 plus 11 is 11. So we have the updated distances. We have the node 0 is 0. Node 1 is 4. Node 2 is infinity. Node 3 is infinity. Node 4 is 11. Node 5 is infinity. Node 6 is infinity. And node 7 is infinity. Number 3, mark node 0 as visited. Step 3. Process node 1. The next node to process is 1, meaning the smallest unvisited distance is 4. Number 2, update the distances to its neighbors. We have the node 4, the distance is equal to 4 plus 8 is equal to 12. The node 4 is, we have the distance is equal to 4 plus 8 is equal to 12, or this is the largest than the current distance of 11. So, no update. So, we have the updated distances. We have node 0 is 0. Node 1 is 4. Node 2 is 12. Node 3 is infinity. Node 4 is 11. Node 5, node 6, and node 7 is infinity. Mark node 1 as visited. Step 4. Process node 4. Number 1. The next node to process is 4, which is the smallest unvisited distance is 11. Number 2. Update the distances to its neighbors. We have the node 5. Our distance is 11 plus 7 is 18. So now we have the updated distances. We have now the node 0 to 0. Node 1 is 4. Node 2 is 12. Node 3 is infinity. Node 4 is 11. Node 5 is 18. Node 6 and node 7 is still infinity. Mark node 4 as visited. Step 5. Process node 2. The next node to process is 2, which is the smallest unvisited distance, 12. Number 2, update the distances to its neighbors. Our node 3 is 2. Distance is equal to 12 plus 7 is equal to 19. Node 5 is distance, 12 plus 6 is 18, which is already 18, no change. So the updated distances we have node 0 is 0, node 1 is 4, node 2 is 12, node 3 is 17, node 4 is 11, node 5 is 18, and still node 6 and node 7 is still infinity. Mark node 2 as visited. Step 6. We already here in process node 5. The next node to process is 5, which is the smallest unvisited distance, 18. Number 2, update the distances to its neighbors. Node 6, we have distance is equal to 18 plus 2 is equal to 20. We have the updated distances. The node 0 is still 0, node 1, 4, node 2, 12, node 3, 19, node 4, 11, node 5, 18, node 6, 20, and node 7 is 20. Mark node 5 as visited. So, in step 7, process node 3. Number 1, we have the next node to process is 3, which is still the smallest unvisited distance, which is 19. We have update, number 2, update the distances to its neighbors. The node 7, distance is equal to 19 plus 9 is 28. So here the updated distances. And number 3 is mark node as visited. So now, in step 8, process node 6. The next node to process is 6. The smallest unvisited distance is 20. Update the distances to its neighbors. We have node 7. The distance is 20 plus 10 is 30, which is the largest than the current distance of 28, so no update. So now here the updated distances, and mark node 6 as visited. The last process, step 9, process node 7. The last node to process is 7.